Time dilation is a fascinating concept that emerges from the realm of physics, particularly within the framework of Einstein's theories of relativity. At its core, time dilation refers to the phenomenon where time passes at different rates for observers in varying states of motion or gravitational fields. This means that time is not a constant, universal measure, but rather a relative experience that can change based on speed and gravity. The significance of time dilation extends beyond theoretical physics. It has profound implications for our understanding of the universe and our place within it. For instance, as an object approaches the speed of light, time for that object slows down relative to a stationary observer. This has been experimentally confirmed through various means, such as observing particles moving at high speeds and the behavior of atomic clocks on fast-moving jets. The relevance of time dilation in physics cannot be overstated, as it challenges our intuitive notions of time, compelling us to rethink the very fabric of reality. The implications of time dilation stretch into our everyday lives in ways that might seem mind-bending at first glance. For example, consider the Global Positioning System, GPS, which relies on satellites orbiting the Earth. These satellites experience time differently than people on the ground due to their high speeds and the weaker gravitational field at their altitude. If the effects of time dilation were not accounted for, GPS calculations would quickly become inaccurate, leading to significant errors in navigation. This practical application of time dilation illustrates how deeply intertwined our daily experiences are with the principles of relativity. Furthermore, the concept invites us to ponder philosophical questions about the nature of time itself. If time can stretch and contract, what does that mean for our understanding of past, present, and future? It challenges the linear perception of time that many of us hold, suggesting that time is more fluid and complex than we might have previously imagined. Setting the stage for a deeper exploration of Einstein's theories, we find ourselves at the intersection of science and philosophy. Einstein's special relativity introduced the idea that the laws of physics are the same for all observers, regardless of their relative motion, leading to the conclusion that time is not absolute. His general relativity further expanded this understanding by incorporating gravity into the equation, showing that massive objects can warp spacetime, causing time to pass more slowly in stronger gravitational fields. These revolutionary ideas have reshaped our comprehension of reality, prompting scientists and thinkers alike to reconsider the nature of existence itself. As we delve into the intricacies of time dilation and its implications, we embark on a journey that not only enhances our grasp of physics, but also invites us to reflect on the very essence of time and how it influences our lives and the universe around us. Time dilation is a concept that fundamentally alters our understanding of time, revealing that it is not a fixed entity, but rather a variable that can change based on certain conditions, particularly speed and gravity. At its essence, time dilation refers to the phenomenon where time passes at different rates for observers, who are in different states of motion or are situated in varying gravitational fields. This means that two observers, one moving at a high velocity and another at rest, will experience time differently. The relationship between speed, gravity, and the flow of time is a cornerstone of modern physics, intricately woven into the fabric of Einstein's theories of relativity. To understand how time dilation occurs, we must first explore the effects of speed. According to Einstein's special theory of relativity, as an object approaches the speed of light, time for that object slows down relative to a stationary observer. This is not merely a theoretical assertion. It has been confirmed through numerous experiments. For instance, particles known as muons, which are created when cosmic rays collide with the Earth's atmosphere, have been observed to live longer than expected when moving at speeds close to the speed of light. If we were to visualize this, imagine a spaceship traveling at near light speed. For the astronauts aboard, time would seem to pass normally. But for someone observing from Earth, the astronauts would age more slowly. This illustrates how speed can warp our perception of time, creating a disconnect between different observers. Gravity also plays a crucial role in time dilation, as described by Einstein's general theory of relativity. According to this theory, massive objects like planets and stars warp the fabric of space-time around them. The stronger the gravitational field, the more pronounced the effect on time. For example, time passes more slowly at sea level, where the gravitational pull of the Earth is stronger, compared to a location high in the atmosphere. This effect has practical implications. Atomic clocks placed at different altitudes have been shown to tick at different rates. To put this into perspective, consider two identical clocks, one placed on the ground and the other on a mountain. The clock on the mountain, being further from the Earth's gravitational influence, will run slightly faster than the one at sea level. This phenomenon, known as gravitational time dilation, highlights how gravity can influence the flow of time. Einstein's theories provide the theoretical foundation for understanding time dilation, fundamentally reshaping our comprehension of the universe. His special theory of relativity, introduced in 1905, established that the laws of physics are the same for all observers, regardless of their relative motion. This led to the realization that time is not an absolute measure, but is relative to the observer's frame of reference. In 1915, Einstein expanded upon this with his general theory, which incorporated gravity into the equation. demonstrating that massive objects can distort space-time and affect the passage of time. Together, these theories reveal a universe where time is intertwined with space, creating a dynamic interplay that challenges our intuitive understanding. To illustrate the concept of time dilation in a more relatable manner, consider the analogy of a race between two friends, Alice and Bob. Alice decides to take a high-speed train that travels close to the speed of light, while Bob remains on the ground, watching her depart. As Alice speeds away, she experiences time normally within her train. But for Bob, who is stationary, time appears to slow down for Alice. When Alice returns from her journey, she finds that she has aged only a few years, while Bob has aged significantly more. This scenario encapsulates the essence of time dilation, demonstrating how relative motion can lead to differing experiences of time. Another analogy involves the concept of a clock on a roller coaster. Imagine a clock mounted on a roller coaster that twists and turns at high speeds. For the riders on the coaster, the clock ticks away as they experience the thrill of the ride. However, for an observer standing still on the ground, the clock appears to tick more slowly due to the high speeds involved. This playful scenario helps to visualize how time can be perceived differently based on motion, reinforcing the idea that time is rather a relative experience. In addition to these analogies, we can also consider the implications of time dilation in the context of space travel. If humanity were to embark on a journey to distant stars at speeds approaching that of light, the astronauts aboard would experience time differently than those remaining on Earth, while years may pass for the travelers. Decades or even centuries could elapse on Earth. This concept, often referred to as the twin paradox, highlights the profound effects of time dilation on human experience and relationships, raising questions about the nature of time and how it shapes our lives. As we delve deeper into the implications of time dilation, we begin to appreciate its significance in both theoretical and practical terms. The relationship between speed, gravity, and the flow of time challenges our conventional understanding of reality, prompting us to reconsider how we perceive the passage of time. Einstein's theories serve as a guiding framework, illuminating the complexities of the universe and revealing the interconnectedness of time and space. In conclusion, time dilation is a remarkable phenomenon that underscores the relativity of time, influenced by both speed and gravity. Through Einstein's groundbreaking theories, we gain insight into how time can stretch and contract, leading to varying experiences for different observers. By employing relatable analogies, we can better grasp the implications of time dilation on our perception of time and its impact on our lives. As we continue to explore the intricacies of time and its relationship, we are reminded of the profound mysteries that lie at the heart of physics and our understanding of reality. Time, it seems, is not merely a linear progression, but a complex tapestry woven into the very fabric of existence, inviting us to ponder the nature of our own experience in the universe we inhabit. The thought experiment involving two clocks on a train platform serves as a compelling illustration of the concept of time dilation, a phenomenon predicted by Einstein's theory of relativity. In this scenario, we imagine a train platform where two identical clocks are synchronized and placed at rest. One clock remains stationary on the platform, while the other is placed on a train that travels at a significant fraction of the speed of light. As the train moves away from the platform, we can observe how time dilation manifests through the behavior of the moving clock compared to the stationary one. To visualize this thought experiment, picture a train traveling at a high speed, say 80% of the speed of light. As the train speeds away from the platform, an observer standing on the platform can see the clock on the train ticking away. However, due to the effects of time dilation, the clock on the moving train will appear to tick more slowly than the clock on the platform. This is a direct consequence of the principles outlined in Einstein's special theory, which states that time is relative and can vary depending on the observer's frame of reference. For the observer on the platform, the moving clock's ticks are stretched out, leading to the conclusion that less time has passed for the clock on the train compared to the one that remains stationary. The significance of this thought experiment lies in its ability to demonstrate measurable time differences that arise from relative motion. When the train eventually comes to a stop and the two clocks are compared, it becomes evident that the clock on the train shows less elapsed time than the clock on the platform. This measurable difference in time serves as a concrete example of time dilation, providing a clear illustration of how motion affects the flow of time. The implications of this experiment extend beyond theoretical discussions. They have been confirmed through various experiments in real-world settings, reinforcing the validity of Einstein's theories. One of the most famous real-world applications of this concept is found in the Global Positioning System, GPS. GPS satellites orbiting the Earth experience both velocity-based time dilation due to their high speeds and gravitational time dilation due to their position in a weaker gravitational field compared to the surface of the Earth. If the effects of time dilation were not accounted for, GPS calculations would quickly become inaccurate, leading to significant errors in navigation. The synchronization of time between satellites and ground stations is crucial for the system's accuracy, and engineers must adjust for the time differences predicted by relativity to ensure precise positioning. This practical application illustrates how a thought experiment can have tangible consequences in our daily lives, highlighting the importance of understanding these concepts in the context of modern technology. Moreover, the thought experiment involving the two clocks on the train platform serves as a gateway to deeper discussions about the nature of time itself. It challenges our intuitive understanding of time as a constant, linear progression, prompting us to reconsider how we perceive the passage of time. The realization that time can be experienced differently based on relative motion invites philosophical inquiries into the nature of reality and our place within it. As we explore the implications of time dilation, we are reminded that our understanding of the universe is continually evolving, shaped by the insights gained from thought experiments and empirical observations. In addition to GPS, time dilation has implications in various fields of science and technology. For instance, particle physics experiments conducted at high-energy particle accelerators, such as the Large Hadron Collider, rely on the principles of time dilation to understand the behavior of subatomic particles. When particles are accelerated to speeds close to the speed of light, their lifetimes appear to increase from the perspective of stationary observers. This phenomenon allows scientists to study particles that would otherwise decay too quickly to be observed, providing valuable insights into the fundamental building blocks of matter. Furthermore, the thought experiment can also be connected to the realm of astrophysics. Consider the scenario of cosmic rays, which are high-energy particles originating from outer space. When these particles collide with the Earth's atmosphere, they produce secondary particles known as muons. Muons have a short lifespan, but when they travel at speeds close to the speed of light, they can reach the Earth's surface before decaying. This observation can be explained through time dilation, as the muons experience time differently than observers on the ground. The ability to detect these particles and study their behavior provides crucial information about the universe and the forces at play within it. As we delve deeper into the implications of the thought experiment involving the two clocks, we begin to appreciate the broader significance of time dilation in our understanding of the universe. It serves as a reminder that our perceptions of time and reality are not as straightforward as they may seem. The interplay between speed, gravity, and the flow of time challenges our conventional notions and invites us to explore the complexities of existence. In conclusion, the thought experiment involving two clocks on a train platform effectively illustrates the concept, of time dilation and its observable effects through moving clocks, by demonstrating measurable time differences between a stationary clock and a moving clock. This experiment reinforces the principles outlined in Einstein's theories of relativity. The real-world applications of time dilation particularly in technologies like GPS and particle physics, highlight the practical significance of these concepts in our daily lives and scientific endeavors. We are reminded of the profound mysteries that lie at the intersection of physics and our understanding of reality, inviting us to ponder the nature and its role in shaping in this end. Time dilation, a fascinating consequence of Einstein's theories of relativity, has practical implications that extend into our everyday lives, often in ways that may not be immediately apparent. While the concept may seem abstract, its effects can be observed in various real-world scenarios, particularly in the realms of space travel, satellite technology, and high-speed travel. By exploring these practical examples, we can gain a deeper understanding of how time dilation influences our experiences and the technologies we rely on. One of the most striking examples of time dilation occurs with astronauts who venture into space. When astronauts travel at high speeds in spacecraft, they experience time differently than people on Earth, according to the principles of special relativity. As an object moves closer to the speed of light, time for that object slows down relative to a stationary observer. This means that astronauts aboard the International Space Station, ISS, which orbits the Earth at approximately 17,500 miles per hour, age more slowly than their earthbound counterparts. To illustrate this effect, consider an astronaut who spends 6 months aboard the ISS. Due to the high velocity of the spacecraft and the weaker gravitational field experienced in low Earth orbit, the astronaut will age slightly less than 6 months during their time in space. In fact, calculations suggest that for every 6 months spent in orbit, an astronaut may age about 0.005 seconds less than someone who remained on Earth. While this difference may seem minuscule, it highlights the tangible effects of time dilation in a context that is increasingly relevant as space travel becomes more common. As humanity looks toward longer missions to Mars and beyond, the implications of time dilation on aging and health will become even more significant, raising questions about how we perceive time and its impact on human life. Another practical application of time dilation can be observed in the Global Positioning System, GPS, a technology that has become integral to modern navigation. GPS satellites orbit the Earth at altitudes of around 20,200 kilometers, approximately 12,550 miles, and travel at speeds of about 14,000 kilometers per hour, approximately 8,700 miles per hour. Due to their high velocities and the weaker gravitational field experienced at their altitude, GPS satellites experience both special and general relativistic time dilation. The effects of time dilation on GPS satellites are significant enough that they must be accounted for to ensure accurate positioning. Without these corrections, The time discrepancies would lead to navigation errors of up to 10 kilometers, about 6 miles, each day. Specifically, the clocks on the satellites tick faster than those on the ground due to gravitational time dilation, which causes time to pass more slowly in stronger gravitational fields, such as that experienced on Earth. The combination of these effects results in about 38 microseconds per day, with the satellite clocks running faster than their Earth-bound counterparts. To maintain the accuracy of GPS, engineers must adjust the satellite clocks before launch, setting them to tick slightly slower than ground-based clocks. This preemptive correction ensures that when the satellites are in orbit, the time discrepancies caused by relativistic effects are minimized, allowing for precise location tracking. The reliance on time dilation corrections in GPS technology underscores the practical importance of understanding this phenomenon in our increasingly interconnected world, where accurate navigation is essential for everything from personal travel to logistics and transportation. Time dilation also has implications for high-speed travel and technology beyond space exploration and satellite systems. As we continue to develop faster modes of transportation, the effects of time dilation become increasingly relevant. For instance, consider the potential future of commercial air travel. While current commercial jets travel at speeds of around 900 kilometers per hour, approximately 560 miles per hour, advancements in technology may lead to the development of hypersonic aircraft capable of traveling at speeds exceeding that of sound or even approaching the speed of light. As these speeds increase, the effects of time dilation will become more pronounced. Passengers aboard such high-speed aircraft would experience time differently than those remaining on the ground. For example, if a hypothetical aircraft were to travel at 90% of the speed of light, the time experienced by passengers would be significantly less than that experienced by people on the ground. This could lead to scenarios where travelers arrive at their destinations having aged less than their friends and family who remained behind. While we are not yet at the point of achieving such speeds in commercial travel, the concept of time dilation raises intriguing questions about the future of transportation and its impact on human experiences. Moreover, the implications of time dilation extend to the realm of technology and communication. As we develop faster communication technologies, such as fiber optic networks and satellite communications, the effects of time dilation must be considered. For instance, signals transmitted between satellites and ground stations can be affected by the relative motion of the satellites, leading to potential delays in communication. Engineers and scientists must account for these relativistic effects to ensure that data is transmitted accurately and efficiently, particularly in applications where timing is critical, such as financial transactions or emergency response systems. In addition to these practical examples, time dilation also invites broader philosophical considerations about the nature of time and our perception of reality. The realization that time can be experienced differently and gravity challenges our intuitive understanding of time as a constant. Linear progression. It prompts us to reflect on how our experiences of time shape our lives and relationships, particularly in an age where technology allows us to traverse vast distances in relatively short periods. As we explore the practical implications of time dilation in everyday life, we begin to appreciate the interconnectedness of science, technology, and human experience. From the aging of astronauts in space to the precise functioning of GPS satellites and the potential for high-speed travel, time dilation is a phenomenon that influences our lives in ways that are both profound and tangible. As we continue to advance our understanding of physics and technology, the implications of time dilation will undoubtedly play a crucial role in shaping the future of transportation, communication, and our understanding of the universe. In conclusion, time dilation is not merely a theoretical concept confined to the realm of physics. It has practical applications that permeate our everyday lives. The experiences of astronauts aging more slowly than their Earth-bound counterparts, the necessary time corrections for GPS satellites, and the potential impact of time dilation on high-speed travel all serve to illustrate the significance of this phenomenon. As we navigate an increasingly complex world, understanding time dilation will be essential for harnessing the power of technology and exploring the mysteries of the universe. Ultimately, time dilation challenges us to rethink our perceptions of time and its role in shaping our experiences, inviting us to consider the profound implications of this remarkable aspect of our reality. The twin paradox is one of the most famous thought experiments in the realm of physics, particularly in the context of Einstein's theory of relativity. It presents a fascinating scenario that illustrates the concept of time dilation and its implications for our understanding of time. The paradox involves a pair of identical twins, often referred to as twin A and twin B, who experience different aging rates due to the effects of time dilation. This thought experiment not only highlights the counterintuitive nature of time, but also serves as a gateway to deeper discussions about the nature of reality and the fabric of space-time. In the classic scenario of the twin paradox, twin A remains on Earth, while twin B embarks on a journey through space at a velocity close to the speed of light. As twin B travels away from Earth, they experience time at a slower rate compared to twin A, who remains stationary. According to the principles of special relativity, time is relative and can vary depending on the observer's frame of reference. For twin B, the journey may feel normal with time passing as it typically would. However, for twin A, observing twin B's journey from Earth, it appears that twin B is aging more slowly due to their high speed. When twin B eventually returns to a significant period, they find that they have aged considerably less than twin A. This leads to the paradox: how can two identical twins experience such different from the same point? The resolution of the twin paradox lies in the understanding of acceleration and the different reference frames experienced by the twins. While twin A remains in an inertial frame of reference 1, that is not accelerating, twin B undergoes acceleration during their journey. When twin B turns around to return to Earth, they experience a change in their frame of reference. This acceleration breaks the symmetry of the situation. As twin B is not in a constant inertial frame like twin A, the effects of time dilation are thus not symmetrical. Twin B's journey involves periods of acceleration which contribute to the overall difference in aging. To clarify this further, consider the journey of twin B in two segments: the outbound journey and the return journey. During the outbound journey, twin B travels away from Earth at a high speed, experiencing time dilation. When twin B reaches a certain point in space and turns around, they undergo acceleration, which alters their frame of reference. This acceleration is crucial because it means that twin B cannot simply be treated as an inertial observer throughout the entire journey. Upon returning to Earth, twin B finds that they have aged less than twin B, who remained in a single inertial frame throughout the entire scenario. This resolution highlights the importance of acceleration and clarifies why the twins do not age at the same rate. The counterintuitive nature of time as experienced by different observers is one of the most striking aspects of the twin paradox. It challenges our intuitive understanding of time as a constant, linear progression. In our everyday experiences, we perceive time as something that flows uniformly for everyone. However, the twin paradox reveals that time is not an absolute measure. It is relative and can vary based on the observer's state of motion. This realization prompts us to reconsider how we perceive time and its implications for our understanding of reality. The implications of the twin paradox extend beyond the realm of thought experiments. They have real-world applications and consequences. For instance, the principles illustrated by the twin paradox are essential for understanding the behavior of particles in high-energy physics experiments. When particles are accelerated to speeds close to the speed of light, they experience time dilation, leading to longer lifetimes than would be expected based on their rest frames. This phenomenon has been observed in particle accelerators, where unstable particles such as muons can travel further than anticipated due to the effects of time dilation. Moreover, the twin paradox serves as a reminder of the complexities of time and space in our universe. It invites us to explore the philosophical implications of time as a relative experience, challenging our notions of simultaneity and the flow of time. The realization that two observers can experience time differently based on their relative motion raises profound questions about the nature of reality and our understanding of existence. In addition to its philosophical implications, the twin paradox also has practical consequences for future space travel. As humanity looks toward long-duration missions to distant planets or even interstellar travel, the effects of time dilation will become increasingly relevant. Astronauts traveling at high speeds may experience significantly less passage of time compared to those remaining on Earth. This raises important considerations for the planning of future space missions, including the psychological and physiological effects on astronauts and their relationships with loved ones back home. Furthermore, the twin paradox highlights the importance of understanding relativistic effects in the context of modern technology. As we develop faster modes of transportation and communication, the principles illustrated by the twin paradox will play a crucial role in ensuring the accuracy and reliability of these systems. For example, as we explore the potential for high-speed travel, such as hypersonic aircraft or even theoretical concepts like warp drives, the effects of time dilation will need to be accounted for to ensure the safety and well-being of passengers. In conclusion, the twin paradox serves as a powerful thought experiment that illustrates the concept of time dilation and its implications for our understanding of time. Through the scenario of two twins experiencing different aging rates due to their relative motion, we gain insight into the counterintuitive nature of time as experienced by different observers. The resolution of the paradox through the consideration of acceleration and reference frames highlights the complexities of time and space. In our universe, as we continue to explore the implications of time dilation in both theoretical and practical contexts, we are reminded of the profound mysteries that lie at the intersection of physics and our understanding of reality. The twin paradox not only challenges our perceptions of time, but also invites us to reflect on the nature of existence and the intricate tapestry of the universe we inhabit. Gravity, a fundamental force of nature, has profound implications not only for the motion of objects in the universe, but also for the very fabric of time itself. According to Einstein's theory of general relativity, gravity affects the flow of time, leading to a phenomenon known as gravitational time dilation. This concept reveals that time does not flow uniformly across the universe. Rather, it is influenced by the strength of gravitational fields. To understand this intricate relationship, we must first explore the equivalence principle, which serves as a cornerstone of general relativity and connects gravity to time dilation. The equivalence principle states that the effects of gravity are locally indistinguishable from acceleration. In simpler terms, if you are in a closed room and cannot see outside, you would not be able to tell whether the force you feel is due to gravity or the acceleration of the room itself. This principle implies that gravity can be thought of as a curvature of space-time caused by mass. As a result, the presence of mass not only influences the motion of objects, but also affects the passage of time. This connection between gravity and time is a fundamental aspect of general relativity, leading to the conclusion that time runs differently in varying gravitational fields. To illustrate how time runs slower in stronger gravitational fields, consider two observers, one located at sea level and another at a high altitude, such as on a mountain. The observer at sea level experiences a stronger gravitational pull from the Earth compared to the observer on the mountain. According to the principles of gravitational time dilation, time will pass more slowly for the observer at sea level than for the one at a higher elevation. This effect, while minuscule in everyday life, has been confirmed through experiments involving highly accurate atomic clocks. When synchronized clocks are placed at different altitudes, the clock at sea level ticks slightly slower than the one at a higher altitude, demonstrating the tangible effects of gravitational time dilation. The implications of gravitational time dilation extend beyond terrestrial examples. They are particularly significant in astronomical contexts. One of the most striking examples can be found in the vicinity of massive celestial bodies, such as black holes. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape their grasp. As an object approaches the event horizon, the boundary surrounding a black hole time for that object appears to slow down relative to an observer far away from the black hole. This means that if an astronaut were to venture close to a black hole and then return, they would find that significantly more time has passed for observers far from themselves. This phenomenon raises intriguing questions about the nature of time, as the extreme gravitational effects near black holes could allow for scenarios where time behaves in ways where time behaves in a ways defy our intuition. Another example of gravitational time dilation can be observed in the context of neutron stars, which are incredibly dense remnants of supernova explosions. Neutron stars possess immense gravitational fields due to their compact mass, leading to significant time dilation effects. If an observer were to orbit a neutron star, they would experience time differently than someone situated far away from the star. The closer the observer is to the neutron star, the more pronounced the effects of time dilation would be. This has implications for the study of pulsars, rapidly rotating neutron stars that emit beams of radiation. The timing of these emissions can be affected by the gravitational field of the neutron star. providing valuable insights into the nature of gravity and the behavior of matter under extreme conditions. Gravitational time dilation also plays a crucial role in the functioning of technologies such as the Global Positioning System, GPS. GPS satellites orbit the Earth at altitudes where the gravitational field is weaker than that experienced on the surface. As a result, the clocks on these satellites tick slightly faster than those on the ground due to gravitational time dilation. To ensure accurate positioning, engineers must account for this difference in time, adjusting the satellite clocks before launch to compensate for the effects of gravity. Without these corrections, GPS calculations would quickly become inaccurate, leading to significant errors in navigation. This practical application of gravitational time dilation underscores the importance of understanding how gravity influences the flow of time in our everyday lives. The implications of gravitational time dilation extend beyond technology and into the realm of cosmology. As we explore the universe, we encounter various gravitational fields that shape the behavior of celestial bodies and the passage of time. For instance, the expansion of the universe itself is influenced by the distribution of mass and energy, leading to variations in gravitational fields across vast distances. This has implications for our understanding of cosmic events, such as the formation of galaxies and the behavior of dark matter. Moreover, gravitational time dilation raises intriguing questions about the nature of time itself. If time is affected by gravity, what does this mean for our understanding of the past, present, and future? The realization that time can flow differently depending on the gravitational context challenges our intuitive notions of time as a linear progression. It invites us to consider the philosophical implications of time as a relative experience, shaped by the forces that govern the universe. In conclusion, gravity profoundly affects the flow of time, leading to the phenomenon of gravitational time dilation. The equivalence principle serves as a foundational concept connecting gravity to time, illustrating how time runs slower in stronger gravitational fields. Through examples such as the effects of gravity on clocks at different altitudes, the behavior of objects near black holes, and the implications for technologies like GPS, we gain insight into the intricate relationship between gravity and time. As we continue to explore the cosmos and deepen our understanding of the fundamental forces that shape our universe, the implications of gravitational time dilation will remain a crucial aspect of our quest to comprehend the nature of reality and the passage of tides of self. Unsawars, you may call with Gurk. You may use see you, we may you, The interplay between gravity and time not only enriches our understanding of physics, but also invites us to reflect on the profound mysteries that lie at the heart of existence. Time dilation is a fascinating phenomenon that becomes particularly pronounced in the realms of high-speed particles and cosmic rays. As predicted by Einstein's theory of relativity, time dilation occurs when objects move at speeds approaching the speed of light, leading to significant differences in the passage of time as experienced by those objects compared to stationary observers. This effect is not merely theoretical. It has been observed and measured in various contexts, particularly in particle accelerators and cosmic ray interactions. We can gain a deeper understanding of how time dilation operates in the universe and its implications for modern physics. In particle accelerators, such as the Large Hadron Collider (LHC) at CERN, particles are accelerated to speeds that are a significant fraction of the speed of light. As these particles gain energy and velocity, the effects of time dilation become increasingly relevant. According to the principles of special relativity, as an object approaches the speed of light, time for that object slows down relative to an observer at rest. This means that particles traveling at high speeds experience time differently than stationary observers. For instance, consider a particle known as a muon, which is an unstable subatomic particle that decays into other particles. Muons have a very short lifespan of about 2.2 microseconds when at rest. However, when muons are produced in high-energy collisions in particle accelerators, they are created with significant kinetic energy and travel at speeds close to the speed of light. Due to time dilation, the muons experience time at a slower rate than an observer on Earth. As a result, they can travel much farther than would be expected based on their rest lifespan. This phenomenon has been experimentally confirmed in particle accelerators, where muons produced in collisions much greater than what their rest lifespan would suggest. The role of time dilation in the behavior of particles at high speeds is crucial for understanding the results of experiments conducted in particle physics. When scientists analyze the outcomes of high-energy collisions, they must account for the time dilation effects experienced by the particles involved. This is particularly important when studying the properties of fundamental particles, such as quarks and leptons, as well as the interactions that govern their behavior. The ability to observe and measure the effects of time dilation and particle accelerators has led to significant advancements in our understanding of the fundamental forces of matter. Cosmic rays provide another compelling example of time dilation effects in nature. Cosmic rays are high-energy particles that originate from outer space and travel at nearly the speed of light. These particles can be protons, atomic nuclei, or even heavier particles. And they constantly bombard the Earth's atmosphere. When cosmic rays collide with atoms in the atmosphere, they produce a cascade of secondary particles, including muons. As with muons produced in particle accelerators, the muons generated by cosmic ray interactions also experience time dilation. When cosmic rays enter the Earth's atmosphere, they create muons that travel toward the surface at speeds close to the speed of light. Due to time dilation, these muons can reach the Earth's surface before they decay, despite their short rest lifespan. In fact, experiments have shown that muons created by cosmic rays can be detected at sea level, even though they should have decayed long before reaching the ground based on their rest lifespan. This observation serves as a natural demonstration of time dilation in action, providing compelling evidence for the predictions of relativity. The importance of time dilation in modern physics experiments cannot be overstated. It plays a critical role in our understanding of fundamental physics and the behavior of particles under extreme conditions. For instance, the effects of time dilation must be considered when designing experiments in particle accelerators. As the high speeds of particles can lead to significant discrepancies in expected outcomes if not accounted for. This understanding has led to the development of sophisticated technologies and methodologies that allow scientists to accurately measure and analyze the behavior of particles at high energies. Moreover, time dilation has implications beyond particle physics. It is essential for understanding the behavior of particles in astrophysics and cosmology. The study of cosmic rays, for example, provides valuable insights into high-energy processes occurring in the universe, such as supernova explosions and the interactions of cosmic rays with interstellar matter. By analyzing the effects of time dilation on cosmic rays, scientists can gain a deeper understanding of the fundamental processes that govern the universe and the forces at play in extreme environments. In addition to its implications for fundamental physics, time dilation also has practical applications in technology. For example, the principles of time dilation are crucial for the functioning of the Global Positioning System, GPS. GPS satellites orbiting the Earth experience both gravitational and velocity-based time dilation, which must be accounted for to ensure accurate positioning. Without these corrections, GPS calculations would quickly become inaccurate, leading to significant errors in navigation. This practical application of time dilation underscores its relevance not only in theoretical physics, but also in everyday technology. As we continue to explore the universe and push the boundaries of our understanding, the role of time dilation in particle accelerators and cosmic rays will remain a vital area of research. The ability to observe and measure the effects of time dilation in high-energy physics. Experiments has profound implications for our understanding of the fundamental forces of nature and the behavior of matter at the smallest scales. It challenges our intuitive notions of time and space, inviting us to reconsider the nature of reality and the intricate tapestry of the universe we inhabit. In conclusion, time dilation is a fundamental aspect of modern physics that is observed in both particle accelerators and cosmic rays. The behavior of particles at high speeds demonstrates the profound effects of time dilation, allowing scientists to explore the properties of fundamental particles and their interactions. Cosmic rays provide a natural example of time dilation in action, illustrating how high-energy particles can defy expectations based on their rest lifespans. The importance of time dilation in modern physics experiments cannot be overstated, as it shapes our understanding of the development of technologies that rely on precise measurements. As we continue to investigate the mysteries of the cosmos, the implications of time dilation will remain a crucial aspect of our quest to comprehend the nature of reality and the fundamental forces that govern our universe. The concept of time dilation, as described by Einstein's theory of relativity, presents both challenges and possibilities for potential interstellar travel, as humanity looks toward the stars. The prospect of traveling at near-light speeds raises profound questions about the nature of time, the feasibility of such journeys, and the philosophical implications of long-duration space missions. By examining these aspects, we can better understand how time dilation could shape the future of interstellar exploration. Traveling at near light speeds presents significant challenges, both technologically and physically. The first hurdle is the immense amount of energy required to accelerate a spacecraft to such velocities. According to the principles of relativity, as an object approaches the speed of light, its mass effectively increases, requiring exponentially more energy to continue accelerating. This means that achieving even a fraction of the speed of light would necessitate advancements in propulsion technology far beyond our current capabilities. Concepts such as nuclear propulsion, antimatter engines, and even theoretical ideas like warp drives or wormholes have been proposed, but each comes with its own set of challenges and uncertainties. In addition to the energy requirements, traveling at near light speeds poses significant risks to the spacecraft and its occupants. At such high velocities, even tiny particles in space could become lethal projectiles, potentially damaging the spacecraft. Shielding against cosmic radiation becomes another critical concern, as prolonged exposure to high-energy particles can have detrimental effects on human health. Moreover, the psychological and physiological effects of long-duration space travel must be considered, as astronauts would be isolated from Earth for extended periods, facing challenges related to mental health, social dynamics, and physical well-being. Despite these challenges, the concept of time dilation offers intriguing possibilities for interstellar travel. Travelers approach the speed of light. They would experience time differently than those remaining on Earth. This effect, often described as a form of time travel into the future, means that while years may pass for the travelers, significantly more time could elapse on Earth. For instance, if a spacecraft were to travel at 99% of the speed of light, the crew aboard could experience only a few years of travel time, while decades or even centuries might pass on Earth. This aspect of time dilation presents a pew with summation, insummation, in the way to see to see to it really, and we say you sleep to free call God first I you see sick I for the fact to I mean I see DXC deep make more this spouse again but it's that has but I beautiful that's news The implications of time dilation as a form of time travel raise profound philosophical questions. If astronauts were to embark on a long-duration mission to a distant star, they would return to find that their loved ones on Earth have aged significantly more than they have. This disparity in aging could lead to complex emotional and social dynamics. As the travelers grapple with the reality of having missed out on years on Earth, the experience of returning to a world that has changed dramatically in their absence could create feelings of isolation, challenging the very nature of relationships and human experience. Moreover, the concept of time dilation invites us to reconsider our understanding of time itself. If time is relative and can be experienced differently, what does this mean for our perception of the past, present, and future? The idea that one could effectively travel into the future by moving at near light speeds challenges our intuitive notions of time as a linear progression. It raises questions about the nature of existence and the significance of our experiences, as the travelers may find themselves in a future that is both familiar and foreign. In addition to the emotional and philosophical implications, long-duration space missions also prompt considerations about the nature of human society and culture. As humanity ventures into the cosmos, the experiences of astronauts on interstellar journeys could lead to the development of new social structures, norms, and values. The isolation of space travel may foster a sense of unity among crew members as they rely on one another for support and companionship. Conversely, the challenges of confinement and the psychological toll of extended missions could lead to conflicts and tensions within the crew. Understanding these dynamics will be crucial for the success of future interstellar missions. Furthermore, the potential for time dilation to affect interstellar travel raises questions about the future of humanity as a whole. If time dilation allows for effective time travel into the future, what does this mean for our understanding of progress and evolution? As travelers return to a world that has advanced in their absence, they may find themselves grappling with the implications of technological and societal changes that have occurred while they were away. This could lead to a re-evaluation of what it means to be human in an ever-evolving universe. The exploration of time dilation and its effects on interstellar travel also intersects with a search for extraterrestrial life. If civilizations elsewhere in the universe are capable of interstellar travel, they may have developed technologies that allow them to navigate the challenges of time dilation. This raises intriguing questions about the potential for contact with advanced civilizations and the implications of such encounters for our understanding of life in the cosmos. In conclusion, the effects of time dilation on potential interstellar travel present both challenges and possibilities for humanity's exploration of the cosmos. While the technological and physical hurdles of traveling at near light speeds are significant, the concept of time dilation offers a unique opportunity for time travel into the future, allowing travelers to reach distant star systems within a human lifetime. However, the philosophical implications of long-duration space missions raise profound questions about the nature of time, relationships, and human society. As we continue to explore the possibilities of interstellar travel, understanding the effects of time dilation will be essential for navigating the complexities of our journey into the stars. The interplay between time, space, and human experience invites us to reflect on our place in the universe and the profound mysteries that lie ahead. Time dilation, a phenomenon rooted in Einstein's theory of relativity, profoundly challenges our understanding of existence and the nature of time itself. As we delve into the intricacies of time dilation, we encounter the relativity of simultaneity, a concept that reshapes our perception of time and compels us to reconsider the very fabric of reality. This exploration not only invites us to reflect on the philosophical implications of time, but also encourages us to think critically about our own experiences of time in our daily lives. At the heart of the discussion on time dilation is the relativity of simultaneity, which posits that events that appear simultaneous to one observer may not be perceived as such by another observer moving at a different velocity. This principle fundamentally alters our understanding of time as a universal constant. For instance, consider two observers, one standing still on Earth and another traveling in a spaceship at a significant fraction of the speed of light. If both observers witness two lightning strikes occurring at opposite ends of a train platform, the observer on the platform may perceive the strikes as simultaneous. However, the observer in the spaceship moving at high speed may see one strike before the other due to the effects of time dilation and the finite speed of light. This discrepancy in the perception of simultaneity illustrates that time is not an absolute measure, but rather a relative experience shaped by the observer's frame of reference. The implications of the relativity of simultaneity extend beyond theoretical physics. They challenge our intuitive understanding of existence. In our everyday lives, we often operate under the assumption that time flows uniformly for everyone, creating a shared experience of reality. However, the realization that time can be experienced differently based on relative motion prompts us to reconsider the nature of our interactions and relationships. If two people can experience the same event in fundamentally different ways, what does that mean for our understanding of shared experiences and collective memory? This question invites us to reflect on the nature of existence itself and how our perceptions shape our understanding of reality. Moreover, the relativity of simultaneity raises profound philosophical questions about the nature of time and existence. If time is not a fixed entity, but rather a fluid and relative experience, what does this mean for our understanding of the past, present, and future? The traditional linear view of time, where events unfold in a sequential manner, is challenged by the idea that different observers may perceive time in vastly different ways. This invites us to explore the concept of time as a dimension that is intertwined with space, leading to the notion of space-time, a four-dimensional continuum where time and space are inextricably linked. The implications of this understanding extend to our perception of existence itself. If time is relative, then our experiences of life, growth, and change are also relative. This raises questions about the nature of identity and continuity. Are we the same person as we were years ago, or do we exist as a series of moments that are shaped by our experiences and perceptions? The fluidity of time challenges the notion of a fixed self, inviting us to consider the dynamic nature of existence and the ways in which our identities are shaped by the passage of time. As we reflect on these philosophical questions, we are encouraged to think critically about our own experiences of time. In our fast-paced modern lives, we often find ourselves caught up in the relentless march of time, measuring our days by schedules, deadlines, and responsibilities. Yet, the experience of time can vary dramatically based on our circumstances and state of mind. Moments of joy, excitement, or deep engagement can seem to fly by, while periods of boredom or distress may stretch on indefinitely. This subjective experience of time highlights the relativity of our perceptions and invites us to consider how we can cultivate a deeper awareness with time. Furthermore, the exploration of time dilation and its implications encourages us to reflect on the nature of our existence in a broader context. As we contemplate the vastness of the universe and the potential for time travel through the effects of time dilation, we are reminded of our place within the cosmos. The realization that time can be experienced differently across vast distances and varying velocities invites us to consider the interconnectedness of all beings and the shared journey of existence. It prompts us to reflect on the significance of our choices, relationships, and experiences as we navigate the complexities of life. In addition to these personal reflections, the challenges posed by time dilation also have implications for our understanding of the universe and the nature of reality. As scientists continue to explore the mysteries of time and space, they are confronted with questions that transcend the boundaries of physics. The interplay between time, gravity, and the fabric of the universe invites us to consider the fundamental nature of existence itself. Are we merely observers in a vast and indifferent cosmos, or do our experiences and perceptions shape the reality we inhabit? These questions challenge us to engage with the philosophical dimensions of our existence and to seek a deeper understanding of the universe and our place within it. As we navigate the complexities of time and existence, it is essential to cultivate a sense of curiosity and wonder about the nature of reality. The exploration of time dilation and the relativity of simultaneity invites us to embrace the unknown and to seek answers to the profound questions that arise from our experiences. By engaging with these concepts, we can develop a richer understanding of ourselves and the world around us, fostering a sense of connection to the broader tapestry of existence. In conclusion, time dilation challenges our understanding of existence by revealing the relativity of time and the complexities of our perceptions. The concept of simultaneity, as illustrated by the principles of relativity, invites us to reconsider our assumptions about shared experiences and collective memory. The philosophical questions raised by the nature of time compel us to reflect on our identities, the fluidity of existence, and the interconnectedness of all beings. As we think critically about our own experiences of time, we are encouraged to cultivate a deeper awareness of our relationship with the passage of time and to embrace the mysteries of existence. Ultimately, the exploration of time dilation serves as a reminder of seeking understanding in our journey through life. In this exploration of time dilation, we have delved into a fascinating and complex phenomenon that challenges our understanding of reality and the nature of time itself. Time dilation, as described by Einstein's theory of relativity, reveals that time is not a fixed entity, but rather a relative experience that can vary based on factors such as speed and gravity. This concept has profound implications for our perception of existence. The behavior of particles in high-energy physics, and even the potential for interstellar travel. One of the key points we discussed is the relativity of simultaneity, which illustrates how events that appear simultaneous to one observer may not be perceived as such by another observer moving at a different velocity. This principle fundamentally alters our intuitive understanding of time, prompting us to reconsider how we perceive shared experiences and collective memory. The realization that time can be experienced differently based on relative motion invites us to reflect on the nature of identity, challenging the notion of a fixed self. We also explored the implications of time dilation in practical contexts, such as particle accelerators and cosmic rays. In particle physics, time dilation allows particles like muons to travel farther than expected due to their high speeds, demonstrating the tangible effects of this phenomenon. Similarly, cosmic rays provide a natural example of time dilation in action. As high-energy particles from space can reach the Earth's surface despite their short lifespans. These observations underscore the importance of time dilation in modern physics experiments and our understanding of the fundamental forces of nature. Furthermore, we examined the potential for time dilation to impact interstellar travel. As humanity looks toward the stars, the prospect of traveling at near-light speeds raises intriguing possibilities for time travel into the future. While the challenges of such journeys are significant, the concept of time dilation offers a unique opportunity for explorers to reach distant star systems within a human lifetime, even if decades or centuries pass on Earth. This aspect of time dilation invites us to reflect on the philosophical implications and the nature of existence itself. As we wrap up this discussion, we encourage you to engage with the content and explore these concepts further. If you found this exploration of time dilation intriguing, consider subscribing to our channel for more thought-provoking discussions on the nature of reality, physics, and the universe. By subscribing, you'll stay updated on our latest videos and be part of a community that seeks to understand the complexities of existence. We also invite you to like this video and share it with friends and family who may be interested in the fascinating world of time dilation and relativity. Sharing knowledge is a powerful way to spark curiosity and encourage meaningful conversations about the nature of time and our place in the universe. Your engagement helps us reach a wider audience and fosters a community of learners eager to explore these profound topics together. Additionally, we encourage you to explore related content on our channel or website. We have a wealth of resources that delve deeper into the principles of relativity, the implications of time dilation, and other captivating topics in physics and cosmology. Whether you're interested in the philosophical questions raised by the nature of time, the practical applications of relativity in technology, or the latest discoveries in astrophysics, there's something for everyone to discover. In conclusion, time dilation is a remarkable phenomenon that challenges our understanding of reality and invites us to reflect on the nature of existence. By engaging with these concepts, we can develop a richer understanding of ourselves and the universe around us. We hope this discussion has sparked your curiosity and inspired you to continue exploring the mysteries of time and space. Thank you for joining us on this journey, and we look forward to sharing more insights and discoveries with you in the future.